Hey everyone, how's it going? Hey Leo. Hey Cleo. We're feeling good, feeling pumped. Is this your first bit of revision of the day? Or have you already been working hard? I haven't. I did one other session on the, I just did a session on the Snap Revise website. And before that, well, yeah, that was mainly just in bed. Still in bed. Oh, well, that's kind of a good effort. I should start doing these sessions from in bed. I don't know, I think it'd be too difficult to do the writing. Oh. Hey Summer, hey Miriam. You all pumped? Yeah, I am not bad. I've just found out that my a piece of work I was working on has got accepted for a little online talk at a conference, so I'm in quite a good mood today. That's not most days that happens, so yeah, it's nice. Wasn't enough to get me out of bed at a reasonable time, but it was enough to kind of lay there in a daze, being happy for a bit. Yeah, me too. Yeah, funnily enough, it's going to be basically exactly like this. We're going to do, it's all going to be done on YouTube, etc. Yeah, this stuff works really well, the kind of streaming through YouTube. Very reliable. And how is everyone else doing? Is everyone else just woken up and just can't stop loving physics? It's got to be it, right? I'll take a mare. A mare isn't a no. So yeah, I'll take it. Yeah, it's all right. Hey, Hashini. Yeah, it really took me a while to get used to A-level physics. Like I did not take to it quickly at all. First, certainly I remember like first few months, it just felt dreadful and just like way too hard. Okay, so I think we'll get going with the session. So today is all about nuclear decay and the rate of decay. So we're moving on a bit from the revision that we were doing on the particle physics. And you can imagine this to be a bit more like applied particle physics. There's all the stuff about like what's really going on underneath, what everything's made of. And now we're going into the kind of applications, the dangers and the positives of all of these sorts of things. So I'll just share my screen with you so you can see what we've got. So today is about half-lives and nuclear decay. So as always, this is brought to you from SnapRevise. I just came from doing a session like this on SnapRevise, actually. There's a coupon code at the end for if anyone is interested in joining the site and learning their A-level along with us. Okay, so yeah, we have a discount code saved for the end. Now, let's have a go at a question. 18. In a demonstration to her class, a teacher pours popcorn kernels onto a hot surface and waits for them to pop. The kernels pop one by one. There is a large rate of popping at first, and this rate decreases as time goes on. However, the order in which the kernels pop cannot be predicted. How realistic is this demonstration as an analogy to radioactive decay? Consider aspects of the demonstration that are similar to radioactive decay and aspects that are different. Okay, so there's 4 marks, so we're going to want to make 4 points. At least one of them needs to be a similarity with nuclear decay, and one of them needs to be a difference. Does anyone have any ideas? In what way is this group of popcorn kernels like a group of atoms undergoing radioactive decay? Good. So the time at which any particular kernel is going to go off, we can't predict. It seems to be random. Any particle? Good. Good. Okay, so I like this. Kernel popping, like nuclear decay, is random. We cannot know which kernel will pop next. Okay. Okay, so moving away from the randomness for a bit, is there anything else that feels a bit like radioactive decay here? What else have we been told about what happens with these kernels that pop? At first, the rate is high, but then it slows down. Nice. Okay. So why is it high at the start? Why is the rate of kernel popping high at the start? And why is the rate of radioactive decay in a group of radioactive atoms always higher at the start? So for the records, this would indeed earn a mark already. So just saying that the rate of radioactive decay also decreases over time. Just out of interest though, why is the rate of kernel popping so much higher at the start? Yeah, good. There's a load of these kernels that haven't popped yet. And so there's loads more kernels that could pop. And so the rate of popping will be larger at the start. The same way in nuclear decay at the start, there's loads of things that haven't decayed. And so there's a large rate of decaying at the start because there's lots of things that could decay. Good, okay. So rate depends on number of radioactive atoms / unpopped kernels. Okay, fine. So we need a difference. We need a difference between kernel popping and radioactive decay. Can anyone come up with a difference? There's a really important property of radioactivity that it's actually really easy to forget about. But it's really it's quite a startling property. So the kernel popping eventually stops, but decay doesn't. The decay could, in principle, stop. You don't see it in one of those decay graphs, but it absolutely could be that all of the atoms eventually decay. Radioactivity can tell you the age of something. That's true. It's true that it's not clear how you'd use kernel popping to the same effect. That's true. Let's see. I guess, yeah, I guess that's kind of a result of this. So there are some differences between radioactive decay and kernel popping, and as a result, there's some things you can do with one and not the other. I think here we're really looking for a difference in how they behave, in how kernel popping behaves and how radioactive decay behaves. What happens if I turn up the temperature of the hot surface? Yeah, see, again, I'm not so sure because I think it is kind of random. Good. The rate, if I turn up the temperature here, the rate of kernel popping increases. Does anyone know what happens if I turn up the temperature of a radioactive sample? So if I turn up the temperature of a radioactive sample, nothing happens. Yeah, nothing changes. Radioactive decay is independent, and it's easy to forget this fact. It's really worth having in your head. Radioactive decay is independent of any external factors at all. There's nothing I can do. Increasing the pressure won't change the rate of decay or the likelihood of decay. Increasing the temperature won't have any change. So here, clearly, the popping of the kernels here is a result of heating them up. We had to put them on a hot surface to get them to pop. Okay, so difference. Rate of kernel popping. Rate of kernel popping depends on temperature. Radioactive decay does not. Yeah. So this is, again, it's one of those things that appears as like a line in your textbook, but it's really a startling fact. Like, I just can't do anything to speed up the rate of radioactive decay. To me, that's madness. I think it's actually really cool. It's just very surprising to me anyway. Okay. X and Y are two different beta emitting sources. Initially, they contain the same number of unstable nuclei. Both sources have their emissions recorded over a period of time. The decay constant of source X is greater than that of Y. State what is meant by decay constant and describe two differences in the recordings from the two sources. You may be awarded the additional blah marks for writing nicely. Cool. Okay. So can anyone define the decay constant for me? So the decay constant is given the symbol lambda. That may jog some memories. So the decay constant is a measure of how likely it is that any particles decay. Yeah. So in fact, there's two ways of phrasing it. One way of phrasing it is saying it's the probability that any atom will decay in a second. There's another way we can talk about this. We can say the decay constant is given by the rate of decay, which we're going to call A. And okay, well, I'll just write the formula first, divided by the number of atoms in the sample. So let's just pick apart this formula a second. N here represents the number of radioactive atoms in a sample. This is the rate of radioactive decay in that sample. Now, let's be very explicit about this. By rate of radioactive decay, what do I mean? I mean the number of decays happening per second. That's the rate of radioactive decay. Okay, so this is a definition for the decay constant. The decay constant essentially measures how radioactive is this thing. How many decays are going to happen per second. The higher the decay constant, the more radioactive, the more decays this thing is kind of emitting. The more beta particles, for example, this thing is going to emit per second. So initially we're told that these sources contain the same number of unstable nuclei. Okay. State what is meant by decay constant. We did that. And now describe two differences in the recordings from the two sources. So we're going to record the emissions of sample X and sample Y. By record them, we mean we'll use some kind of Geiger counters, which measure each radioactive event that happens. Okay, so what's the difference? If X has a bigger decay constant, what will we see at the start? Which Geiger counter is going to be seeing more radioactive decays? Which one of these materials, material X or material Y, is going to be emitting more beta particles, emitting more radiation at the start? X. Good. X has a bigger decay constant. Now we're told that both of these materials have the same number of unstable nuclei, i.e. they have the same value of N here. So what does that mean? Well, the one with the bigger decay constant will have a bigger rate of radioactive decay. Good, okay. So two differences. At the start, rate of radioactive decay in X will initially be larger than rate in Y. Good. Okay. Some other difference. So can anyone come up with another difference? So this is, I've said initially here, initially. So I've noticed some difference that happens right away as soon as I switch on these Geiger counters and I record what's happening. But they say the sources have their emissions recorded over a period of time. So maybe we can say something about what happens as time goes on. So why do you say that, Leo? And I think that's interesting. It's a really, yeah, this is a good point. Yeah, the rate, since the rate of decay for X is bigger than the rate of decay for Y. What does this mean? Well, as some more particles can decay later on. Yeah, good. So the rate of radioactive decay in X is initially larger. What does that mean? It means that the number of particles here goes down quicker than, let's call this NX, goes down quicker than NY, say the number of particles in Y. Now, if we look at this equation for a second and rearrange it, this says N lambda equals A. Now, what that says is that the number of particles is proportional to the rate of decay, the number of decays happening per second. Now, since the number of particles that X has is dropping more quickly because it's going through more decays, that also means that it's, if the number of particles is dropping more quickly, the rate at which it's decaying must also be dropping more quickly, because the rate is entirely determined by the number of particles. So let's find a nice way to phrase this. So the count rate is another way of saying the rate of radioactive decay. The count rate for X decreases more rapidly than the count rate for Y. Good. Okay. So those are two differences that you'll see when you switch on these Geiger counters and really record what's happening. Good. Okay. Let's have a go at a more mathematical question now. The radioactive isotope of sodium, given by some specific numbers, has a half-life of 2.6 years. A particular sample of this isotope has an initial activity of 5.5 times 10 to the 5 becquerels. So these are the units for activity, the number of decays per second. Explain what is meant by the random nature of radioactive decay. Okay, so we won't use these numbers quite yet. First of all, this is very similar to that first question. So charge some facts at me. We need two ways in which radioactive decay has a random nature. Good. It is impossible to know which atom will next decay. Yeah, and you also don't know what time any particular particle will decay. It is impossible to know at what time any particle will decay. Good. Okay. So now we will probably be asked to do some more mathematical stuff. So use the axes to sketch a graph of the activity of the sample of sodium over a period of 6 years. Okay, so before doing anything, what is the one point that we can plot? What is the activity at time equals 0? Good. So we've been told in the question it has an initial activity. So that's the activity at time equals 0 of 5.5 times 10 to the 5. Good. So let's plot that in. That's just here. Now, we want to somehow draw how the graph looks. Now, does anyone know roughly how it looks? And is there any information that will allow us to be more precise here? What piece of information are we going to use to plot some other points on this graph? The half-life. Yeah. So this thing, the activity depends entirely on the number of particles. As radioactive decay happens, then the number of radioactive particles decreases. And if there's less particles around to decay, the activity itself will decrease too. So this thing is just going to go down as time goes on. But I want to plot some extra points. And this suggestion of a half-life is going to help us. So the half-life is what? 2.6 years. So after 2.6 years, what's the activity going to be? What does half-life mean? Half-life is the time taken for the activity to go down to half of its initial value. Good. So we're looking for half of 5.5, which is, or what is half of 5.5? 2.75, isn't it? Good. Yeah. So let's find that on here. 2.5, 2.75. It's going to be around here, isn't it? Okay, so I think we've found our first point. Okay, so now we get the principle. Can anyone suggest another point to me that we can have on this graph? Give me the X and Y coordinate of this point. Good. So if we, absolutely right. Good. So together we've got a new point. Absolutely right. We go for a whole nother half-life. Another half-life would take us to 5.2 years. Good. After 5.2 years, we know we need to halve what we have again, which is going to be around 1.4. So where's 1.4? That's about here, isn't it? 1.4. Good. There we go. So that's as many points as I think we can actually try and plot here. Of course, that's not the best line I ever drew, but that's the answer they're looking for. Good. Well done, everyone. Those good answers there. Now we're asked to do some more stuff. Calculate the decay constant in seconds to the -1. So now we know the decay constant was this quantity lambda. We already gave a definition of it in terms of activity over number of particles. We haven't been told, we've been told activity. I don't think we've been told number of particles. So this looks a bit hard. Does anyone know any other formulas? We need another formula for the decay constant. Good question. I don't immediately know off the top of my head, sorry. Sorry, I'm not sure off the top of my head. I think OCR need this. I can't remember, sorry. I expect so though. Definitely one of them will. Yeah. So the other formula that we're looking for the decay constant is a formula that's entirely in terms of the half-life. So I have a formula between the decay constant and the half-life. Let's call it T half, which we've been told. We've been told the half-life is 2.6 years. So the formula we're looking for is the following. It says that the decay constant is equal to ln 2, so the natural logarithm of 2 divided by the half-life. Okay. So they want this thing in kind of second-like units. So we probably need to take these years and convert them into seconds. So 1 year is 3.15 times 10 to the 7 seconds. We've got 2.6 years as the half-life. So 2.6 times 3.15 times 10 to the 7 seconds. Then the decay constant is equal to ln 2 divided by 2.6 times 3.15 times 10 to the 7. And if you chuck that into your calculator, you should get 8.5 times 10 to the minus 9. And seeing as this was in seconds, the units of this thing here are indeed seconds to the power minus 1. Good. So this is a really useful formula. It's a very cheeky formula, this one, because it's, again, easy to forget. But often it feels like you haven't been given enough information, and that's because you need to use this formula. Good. Calculate the number of atoms in the sample initially. So remember, we now have a new fact. We know this decay constant is equal to 8.5 times 10 to the minus 9. So how can we find the number of atoms from the information we've been given here? What equation could we use? We've been told a decay constant and we've been told an activity. Is there an equation that relates the activity, the decay constant, and the number of atoms? Good, yeah, okay, so we had this formula before. The decay constant is equal to the activity divided by the number of particles. We want to know the number of particles. Great, okay, so that's n equals a divided by lambda. And in fact, we've been told both of these quantities because they want to know the number of atoms initially, and we know the initial activity. So that's perfect. We've actually got the right number here. Cool. So n is equal to 5.5 times 10 to the power 5 divided by 8.5 times 10 to the power minus 9. And if we chuck that into a calculator, we should get around 6.5 times 10 to the 11. That's a lot of particles. What are they? They're not just any old particles, these are atoms. So yeah, it's a lot. Good, absolutely right. So we wanted to use A over lambda here. Nice one. So let's try another question. And I know someone right at the start mentioned some stuff about radioactive dating and aging. So maybe this is a chance to chat a bit more about that. The age of an ancient boat may be determined by comparing the radioactive decay of that particular isotope of carbon from living wood with that of wood taken from the ancient boat. Okay, so there's going to be some kind of difference between the radioactive decay of this isotope in normal wood and this ancient boat. Odd. A sample of 3 × 10⁻23 atoms of carbon is removed for investigation from a block of living wood. In living wood, 1 in 12 of the carbon atoms is the radioactive isotope, this one, which has a decay constant of this much. Calculate the half-life in years, giving your answer to an appropriate number of significant figures. So how can I calculate the half-life from the information I've been given here? What do I know? Let's start. Whenever you read a question like this, it's helpful to start giving symbols to the quantities that you've been given. So, does anyone recognize anything here? Good. Yeah, really nice stuff. So, here we've got a lambda. Okay. Here, maybe we've got some kind of an n. We won't worry about that for now because a lambda is always enough. As soon as you've got lambda, you've got the half-life. As soon as you've got the half-life, you've got the decay constant. Why? Exactly right. Because the half-life is equal to the natural log of 2 divided by the decay constant. So we actually have everything we need already. Ln 2 divided by 3.84 times 10 to the minus 12. Okay, so we can chuck this into our calculator and we should get around 1.0805 times 10 to the 11 times 10 to the power 11. And what have we done here? We've done everything in seconds. So what's wrong with my answer at the moment? Well, they asked me to calculate it in years. So now I need to figure out how many years I have. Well, if 1 year is 3.15 times 10 to 7 seconds, then I can find the number of years I have by dividing by that amount. Times 10 to the 11 divided by 3.15 times 10 to the 7. And if we do this, we should find 5,730 years. Cool. So we think we know the half-life of this material. It's quite long, 5,000 or so years. Okay, so let's see if we end up using this information. Show that the rate of decay of the C14-6 atoms in the living wood sample is 1.15 becquerels. Okay, so show the rate of decay is this much. How are we going to find the rate of decay? The rate of decay. So again, in these radioactivity questions, it's really worth giving everything a symbol. Rate of decay, that's the activity. They mean A. We've been told lambda. Huh. Okay, so if only we knew n, we'd be looking good here. If we knew n and lambda, we'd know A. So what's n? What's the number of C14-6 atoms? Good, you're absolutely right. We are going to use A equals lambda n. So what's n? So this is an interesting question. I'm going to give you another 10 seconds to kind of read carefully through this question because there's an extra cheeky fact here. Because what is n? N is the number of radioactive particles. The number of radioactive particles. So, how many particles do we have, and how many of them are these radioactive particles? The thing that's decaying here is these C14 atoms. Do we have 3 times 10 to the 23 C14 atoms waiting around to decay? Not quite. That's the number of carbon atoms just around. Not all of those are C14. How many of them are C14? Yeah, so when we use this formula, this is rate of decay of radioactive atoms. This is the number of radioactive atoms. Good. So, good. Really good point. In living wood, 1 in 10 to the 12 of these atoms is this particular isotope, the radioactive one. So we might have 3 times 10 to the 3 atoms, but how many radioactive ones do we have? How many of this isotope that we care about do we have? Well, only 1 in 10 to the 12 of them are. So we have to divide by 10 to the 12. So this is quite cheeky. N is equal to 3 times 10 to the 3. Yes, exactly right. Good. Okay. So N is equal to, well, we have 3 times 10 to the 23 atoms, but only 1 10 to the 12th of them are actually radioactive. And so in fact, N is equal to 3 times 10 to the 11. Now, if we want to find the activity, now we're looking good because we know lambda and we really truly know the actual N. So A is equal to lambda N, which is equal to 3.84 times 10 to the minus 12 multiplied by 3 times 10 to the power 11. If you plug that into your calculator, you should get around 1.15 becquerels. Good. Okay, so yeah, that's quite a cheeky question. This piece of information here was lurking around in the background, but was very important for the question. Good thing is it was a show that question. So you'd have got the wrong power and you would kind of realize that something was wrong. So if you get kind of the right answer, like you'd have got 1.15 with a load of other powers on it, that's a good sign that you should look back at the question because there might be a small piece of information that was missed. Good. Okay, finally, we're asked to give 2 reasons why it is difficult to obtain a reliable age of the ancient boat from the carbon dating described. So what might make this method of aging a boat unreliable? So the idea is that they're aging this boat by figuring out how many of these C14 atoms they think are left. Sorry, I think I've missed a question. No, I haven't. We really went straight to E. Yeah, good. Okay. So 2 reasons why this sort of aging would be difficult. So this is a very general question about carbon dating. Might be no C atoms left. So what do you think about the size of this? Has anyone seen these kind of sized activities before? Does it seem like a lot? How many becquerels? A becquerel is like, so what's that, like a decay per second? That's not very much. So what could be the problem if the rate of decay is really slow? So 1 per second, I think the problem is that compared with just like general background radiation, this isn't so much. So we can look it up, in fact. Why don't we do this? Activity of background radiation. Average, maybe. Okay. Well, compared to a couple of becquerels, it's not so, this is around kind of background radiation. This is our problem here. So if the thing that we're trying to measure has a similar kind of value to background radiation, or is kind of comparable, what kind of issue does that bring up? Sorry, I forgot to actually put us onto the question on this page. So give 2 reasons why it's difficult to obtain a reliable age. So the first thing to say is that the background radiation could have a high activity in comparison to the activity we are trying to measure. So this is problematic because it will give us big errors. Like if we're trying to measure the activity and we find that it's half and it's 1 becquerel or whatever, and the background radiation is kind of varying a couple of becquerels either side, then it's going to be really hard to tell. It's going to be really hard to see through all this noise what the actual activity is. So that's a problem. Can anyone think of any other issues that we might have? Yeah, in general, this low activity. Yeah, with low activity, there's kind of a large, with like low sample sizes, there's a large kind of statistical variation in the recorded results. This is true. Yeah. So it's a similar point, but we can absolutely have it as a separate mark. Low activity means large statistical variation in results. Okay, I want to come up with a third thing. And it's going to be a bit more about the context here. So the age of an ancient boat may be determined by comparing the radioactive decay in living wood to that taken from the ancient boat. Okay. So what's the idea here? The idea here, you may have come across this at GCSE or A level, is that you can age things by the number of carbon-14 by the amount of carbon-14 they've got in them. The reason for this is that living things keep on taking in carbon-14, but once things essentially die, then they stop taking it in, but it starts decaying, but it still decays. Now, here's a thing. We're trying to age this boat. Presumably that means when this boat was made. But we have no idea whether that's when the wood was gathered from a tree. Is that when the tree was killed? It could well be that the tree was killed. Yeah, it could be that the wood didn't die straight away. It also could be the other way. It could be that this wood had already been being used for thousands of years, and then they used it to make this boat. Here they're trying to age the boat, not the wood. So wood may have been obtained from tree way before boat was made. In particular, if in these ancient times they were particularly keen on recycling, this would be a nightmare. You couldn't age an object by the things it was made of, because these things have been moving around from different objects for hundreds of years anyway. Okay. So really well done, everyone. Thanks very much for coming to the session and giving me your answers. It's kind of nice to move away from abstract particle physics and go into the applications. I really like the particle physics. In fact, it's part of what I'm interested in research-wise, but this is it's nice to see that the applications, I think. So yeah, thanks very much for coming. As I promised, there will be a code at the end for anyone who wants to join us and come to more of these sessions on the SnapRevise website. Now, I'm just going to give a little walkthrough for anyone who would like to see how SnapRevise works, so I can give you an idea of what we're actually doing on the website. Yeah, thanks very much for coming. And then at the end of that, I'll drop the code for everyone to see. Cool. So I'll just take us through SnapRevise right now. Where's it gone? There we go. Good. So yeah, I'd love to give you a little walkthrough of how SnapRevise works. First of all, I'm doing a load of sessions on SnapRevise at the moment. Yeah, thanks very much for coming. And the idea is quite often very much like this. We do kind of web class sessions where I sit here and I work with people. We have sessions where I have set material that I go through with people and we discuss. And we also have kind of free-form sessions like drop-ins where people can just come in with stuff they've been struggling with. And we as a group will go through the questions together and make sense of them and try and get you a satisfactory answer. So the idea is to kind of capture the idea of private tutoring, but at a fraction of the cost. So let's take a look at my courses, because it's not just the tutoring side of things. There's a lot going on. So let's start off by looking at AQA A-level physics. So let's say I'm interested in seeing how I'm getting on with particles and radiation. This seems like a good example. Sadly, I've done a lot of the quizzes already, so that's sad. Let's do some particle physics then. Well, maybe let's do some particle physics. So hadrons and leptons, why not? We do a quick quiz. Now, the point in the quiz is not just to kind of let us know how we're getting on. I mean, that is part of it, but a big part of the quiz is to try and make a course that's tailored towards us. The idea is that it's very easy to keep going through your textbook or keep going through an online video course. And it's very comforting. Yeah, it's very comforting to kind of look at the stuff that you already know and you kind of feel like you're learning. What you really want to be doing is always looking at the stuff that you don't get, because that's the important stuff. That's where you're really going to make progress and then kind of increase your grades. So let's have a go at this quiz, and this quiz is going to help us figure out what we need to learn in the future. And it's going to make a new course for us. How many fundamental forces are there in the universe? Okay, what do we reckon? I reckon that's 4. Cool. What is the range of the gravitational and electromagnetic forces? That's infinite for both. Now I'll make sure I get a couple wrong as well. So approximate strength. Wow, see this I can't remember off the top of my head. Good, okay. What was the range of the weak nuclear force? What do you reckon? Is it that one? Yeah. Best describes hadrons. So I know full well it's those that have a strong nuclear force. Let's lie. Yeah. Let's make sure we don't know some stuff. Not felt by leptons. Good. Okay. Let's just say something random. And let's just go randomly from here. So we get to see the other side, because that's where the cool stuff happens. Good. Right, so I got exactly 50% right. Fine. Now, there's some nice stats here. There's some stuff that says what I know and what I don't. On its own, this would be kind of useful, but it's easily forgettable. But what if your course was now based on these results? So now I go into Snap Revise and I've got all the video courses, all of the video course available to me. But what I have highlighted over here in my course is things that claim to be completed. These are things for which I did the quiz and I smashed all the questions, so I don't need to learn this video. But I've got the stuff that's important for me highlighted in orange. So as you can see here, there's 3 videos that it thinks I really ought to take a look at based on my quiz results. So I click on these videos, and even inside the videos, so now I get to learn about the thing that I got wrong in the quiz. Not only that, but it highlights in green the bit of the video which I actually already smashed anyway, because even inside the video, there might have been a couple of questions corresponding to that video. So I need to watch up to here to get myself up to scratch. And then similarly, if I go into another video, let's see, this one, yeah, I need to watch the bit on hadrons. I got the bit on leptons correct. Good. So the idea, we call this like a smart adaptive learning when it comes up in the plans. Essentially, the idea is we want to streamline the learning so that you spend less time learning stuff that you know and either more time revising stuff that you don't or more time to chill. So yeah, this is our idea. Try and streamline your learning. We produce separate revision guides as well and exam walkthrough videos. So in this, rather than just kind of producing some exam questions and some mark schemes, the idea is, well, looking at an exam question and mark scheme is useful, but often it's hard to see how the examiner thinks that you should get from the question to the answer. Like often a big part of the question is you know the stuff, but you don't know how to figure out what the examiner wants from the question. So the idea in our exam style question walkthrough videos is that we actually take a look through the questions ourselves and we video ourselves going through the questions, and we give you our personal thought processes behind how we would try and figure out what the question is looking for from us. Great. So I'll just give you a little look at the plans so you can see what we've been up to. So the idea for us was the following. We figured like some really high quality tutors often cost up to £50 an hour. In fact, I've charged this sort of price in private tutoring. Now, this kind of cost is completely inaccessible for a lot of people. So we thought, can we take the idea of a personal tutor and make something which we think is maybe better and more affordable for more people? So we figured rather than £50 an hour, let's produce 3 plans. Each of these plans is not per hour, but per month. So you get way more than you would with like a private tutor. So for either £10 a month, £30 a month, or £50 a month, you get different things. For £10 a month, you get access to our course. We're really happy with the course. You can go through, you can look at all our videos, and you can learn. You can learn from us. I, for example, actually recorded the GCSE physics course. As you can see, someone else did the A-level one. So you have access to all the videos and the exam walkthrough questions as well. For £30 a month, then you have access to this quiz system, which keeps track of your learning and keeps adapting the course around you to try and streamline what you're learning and how much time you're spending on various subjects. Good. So that's a smart adaptive learning feature. We also put together exam packs of the kinds of exam questions that we expect to see coming in the future. So we call them predicted exam packs, and you get access to those. Finally, for the £50 a month version, here you have access to our web classes. So today I did a web class here on YouTube. I'm currently doing lots more web classes on the Snap Revise website as well. So in fact, just before this 11 till 12, I did one on gravitational potential energy and gravitational potential. And not only do we have these kind of web class videos where I kind of teach a lesson and we discuss and do some exam questions together, we also have sessions, as I mentioned before, these drop-in tutor sessions you can access, where I will essentially just be available, and you can send me questions and we go through them together as a group to try and clear up the stuff that you're struggling with. Good. So this is Snap Revise. Thank you so much, everyone, for coming. And really good to see some new and old faces today. And I look forward to seeing you all in the next coming sessions in the future, either on YouTube or on Snap Revise. So just to give you the outlook for what's coming up, we've got more sessions coming on YouTube as well. So here are the home study clubs coming on YouTube, along with way more that are on Snap Revise. So yeah, set yourself a reminder. And here is your code. Great. Thanks very much, everyone. Thanks for coming. And yeah, see you all next time. Cheers. Yeah, bye. No worries. Thanks so much, Takia. Thanks for coming. Cool. Okay, great. Thanks very much for coming, everyone, and see you in the next sessions. Bye.